HU5, the Patti-Salam, and the model that we use is the left-right symmetric model, which was first derived in the free fermionic formulation, at least, by Alan and Gerald and Christopher Savage as well. So we assign our generating fermions these boundary conditions in order to get this left-right symmetric symmetry from our SO10. The additional U1 is external to our SO10 and is generated by the right-moving eta bars. The bar just indicates that they're right-moving fermions. Now, the advantage of breaking to the left-right symmetric model is that we can, the states that are charged under the different SU2s acquire a different sign under our U1. If our model was embedded, say, in E6, we would have to choose one of these signs. And so we couldn't have this charge assignment. Now, we'll take advantage of this because it actually allows for us to have an anomaly-free U1 down to low scales. So if we only include the MSSM in our model, the MSSM states, we see that we have two anomalies induced. Now, we have to look at what string states are required in order to remove these anomalies from the model. And so the additional states, as well as the MSSM, are that we have some extra SU2 doublets in order to cancel our gauge anomalies. In fact, once we add our SU2 doublets, all gauge anomalies are removed. We require a heavy Higgs in order to break our SU2R symmetry. That'll break at some intermediate scale and give us our hypercharge embedding, and the orthogonal combination will give us our light U1. We have singlets in the model from the string states that will allow us to incorporate a type 3 seesaw mechanism in the model. And we also have additional color triplets that originate from twisted planes, as do these doublets. However, these must originate from different twisted planes. We add these, so we allow these to survive in order to slow down the running for our gauge coupling unification. Obviously, the addition of doublets will make us hit a Landau pole very quickly. So we need to slow down the running somehow. And so the analysis, the gauge coupling analysis in free fermionic models was done in this paper. Alan and Keith analysed threshold corrections. And so in terms of our model, we are at, or at least we're very close to the free fermionic point, and so string threshold corrections don't play a big part here. The only threshold corrections that we may stumble upon come from the SU2R breaking, and we, as a first approximation, we treat these as a step function in order to just get an sort of order. What order does new physics essentially appear? So, so these are our intermediate scales. We also have an intermediate scale at which our triplets acquire mass. Now, in this paper, it was shown that an intermediate mass scale is desirable in these models due to the fact, in order to explain the discrepancy between the gut scale of the MSSM and the string scale. So in our model, we do in fact have string scale unification, and it's thanks to our sort of intermediate intermediate mass scales that assist with that. So this is the mass scale hierarchy that we'll have. And so if we run the RGEs from MS to MZ through our intermediate scales, and using our hypercharge embedding and the fact that we will have string scale unification, we use the canonical normalization of alpha 1 because we're in SO10. We do in fact see that we have models that are phenomenologically viable. So this is alpha strong, not a string. So this plot actually shows at various values of alpha string. So if we in fact specify a value of alpha string, the one I chose was, we chose G string to be 0.8 at the unification scale, and it turned out that this region here will be a phenomenologically viable region and will result in the intermediate scales between these sort of levels. Now, unfortunately, the scale of new physics is well beyond the capabilities of the LHC. But I mean, there was no way of seeing this beforehand. So to conclude, hopefully I've convinced you that there at least is a class of models where we have an external U1 from the SO10 that doesn't need to be embedded into E6 that will protect the proton lifetime. I've shown that in this model we get string unification with new physics at sort of 10 to the 6, 10 to the 7 GeV. The question will be in future work whether any interesting phenomenology will result from this due to the fact we have many additional fields, and also what sort of what influence this will have on our Higgs sector. Okay, thanks for listening.
Any questions? So you still have sufficient suppression for the proton
Yes.
creating?
Yeah, so they'll still be sufficiently suppressed. In fact, the bound is something like the coupling needs to be, the product of the couplings needs to be around 10 to the minus 27. And in fact, we'll get something of order about 10 to the minus 28. So it's certainly sufficiently suppressed, even with such a high scale.
And what's the mass scale of the lepton, the extra lepton that you have?
The doublets.
Yeah.
So they'll break with the Z prime because they're required to survive until that level to keep it anomaly free.
All right, so let's thank Viraf again.